pretty.
Well, it's a very great pleasure to introduce our speaker tonight, Dr. Noam Izenberg from the Johns Hopkins University Applied Physics Laboratory. He obtained his PhD at Brown University. His thesis involved making geologic maps of Mars. He then worked at Washington University in St. Louis and has been a planetary scientist at Johns Hopkins University Applied Physics Laboratory ever since 1997. Much of his research has analyzed the processes that occur on the surfaces of the terrestrial planets, Mars and Venus, and sometimes the Earth, and on the surfaces of asteroids. He also measured the oxidation of basalt in the Venus-like atmosphere in the laboratory, and used the results to infer the composition at particular sites on Venus's surface. For his work on Mars, he used data on images and spectra obtained by the Phobos 2 spacecraft, and for Venus, he used emission and radar data from the Magellan spacecraft. For the Earth, he used radar data to study erosion in the deposit of sand during the flooding of the Missouri River in 1993. So that's, you've got all of the terrestrial planets there.
Yep.
At the Johns Hopkins University Applied Physics Lab, he began his research on the surfaces and satellites of asteroids, using data from the flyby of 253 Matilda, and then of 433 Eros, using the NEAR, which stands for the Near Earth Asteroid Rendezvous spacecraft. Dr. Izenberg has also developed new kinds of detectors for measuring and studying the atmosphere of planets, moons, and active comets. He's been an instrument scientist on the NEAR Shoemaker mission to the asteroid 433 Eros and the Messenger mission to Mercury. And he's the deputy chair of NASA's Venus Exploration Analysis Group. He's leading an exoplanet identifier space telescope study at APL, which is one of the things he'll be telling us about. Dr. Izenberg.
Thanks. Thanks for having me. I think I've got as good as I'm going to be able to get for this projection, so please forgive me for all the technical issues we've had getting this up. Hopefully you can see it well. Thanks for the introduction. Yeah, I've been at the Applied Physics Laboratory now for almost 21 years, and I started there as a postdoc working on Near Asteroid Rendezvous mission, and I've been working from graduate school through most of my career on studying the surfaces of planets and small bodies in the inner solar system, and primarily focusing on small bodies like Eros, the planets Mercury and Venus and Earth in various degrees, a little bit on Mars. I have some interests now expanding into the icy satellites of our solar system and the ice giants as well. But it was really in the last few years the rapidly growing field of exoplanets has of course been grabbing the interest of astronomers and planetary scientists all over, and I was asked a couple years ago to give a talk to the National Academies about how understanding the inner solar system in particular, but I guess in general the planets of our solar system, can be used as sort of a gateway to helping to understand the exoplanets that we're discovering and learning more about. So I put together a talk about linking the study of our own solar system, especially the planets closest to us, the planets of the inner solar system, and how that is how that maps, how comparative planetology of our planets is important and translates into helping to better understand the exoplanets we're discovering and learning little bits and pieces about. And from that, it parlayed into a little project that we're having funded within APL and internal research on whether or not you can sort of diagnostically separate Earth-like planets, Earth-like exoplanets, from other types of exoplanets, just using a very simple and maybe less expensive type of telescope than some of the giant, really complex telescopes being planned for our future, and also things like JWST. So this is sort of a two-part talk, and the first thing I want to do, let's see if I can figure out how to do this right. There we go. Just to sort of frame it, what is comparative planetology, right? So I'm coming at what is essentially at the moment mostly an astronomical endeavor from a very planetocentric point of view. Comparative planetology, and because exoplanets, even though we can only find them, we can only see them telescopically, not even as barely, we've gotten one or two or three actually resolved observations of exoplanets from observations from our telescopes. But all of the information most of the information, the vast majority of information we have about exoplanets comes from other methods like transits across a star, or radial velocity measurements, or various other things. So direct observation is not yet a major way that we discover or study exoplanets. But they are still planets, and the need to understand them from the context of the planets that we know, I think, is something that allows exoplanetary astronomers and planetary scientists and requires them to begin to talk to each other and understand how the different ways these objects are studied are done in the different communities. So, comparative planetology is the study of planetary processes, their manifestation, their effects on all the different bodies. We often, at least in our solar system, we use Earth as a baseline because that's what we understand the best. And of course, all these different processes that we think about for the Earth: geology, hydrology, atmospheric sciences, surface processes, interior processes. These are all the sciences and the approaches that we use to study the planets of our own solar system, and thinking about on the bottom habitability and biology or astrobiology. That is, in many ways, that is the ultimate question. That is one of the capital reasons for people searching for exoplanets. We are looking for all kinds of things, but we really are looking for the next Earth. We're looking for another planet like ours. So understanding our planet and how it is unique in our own solar system is one of those crucial aspects of comparative planetology. So we know most about the Earth, right? But relative to the exoplanets, we know far more about even the planets we've only flown by once. We know far more about Neptune or Uranus than we know about any of the exoplanets, because Voyager flew by them. It was decades ago now, but that baseline of information still sort of outstrips the direct knowledge we have of any other exoplanet. Laurie Glaze, who's now the head of the science mission director at NASA, had a great quote. So, as we discover new planets, the only basis we have for comparison are the planets in our own solar system. So this is the starting point for using our planets as a gateway or as a linchpin for studying exoplanets. And I want to. This cartoonish view of how planets evolve is one of the ways that we can approach this. So I want you to think about planetary evolution not in the classic sense of like the accretionary disk collapsing into planetesimals and stuff like that. Think for a minute about if you were standing off at a great distance and could see a planet, what would you see from a telescope? What would the reflected light from that planet be representing? So a very, very young planet, just hot off accretion, is basically just a bunch of hot rock. It could even be molten. It could be a sort of magma ocean on the surface. If it's degassing, you see hot clouds. If cometary or other waters coming out of the out of the rocks from circulation and from condensation of the young planet, you'll see wet clouds or clouds with a lot of water. You might, if there's a lot of water or a lot of cometary material coming into that planet, you might end up with a water planet and something that is there a pointer? No worries.
I have one.
Oh.
I think. Yeah.
All right. Great.
Okay, just a button.
I'll try not to zap it too much, but there we go. So one possible path of a really water-rich early planet is a water-covered planet or an ice planet. If you have a little bit less water, so you have a drier planet, kind of like an early Earth, you can end up with an Earth sort of going to a water and rock mixture of the Earth. If you get even older and you evolve even farther, if you're close to the star, you can end up losing your atmosphere and end up again with hot rock. Think about an Earth-sized, or think about a Mercury-like planet, or a planet like Mars that's closer to the sun and has lost its atmosphere. If you think about something that's farther from the sun, you can and it losing the atmosphere, you can get ice and rock, or the ice can be sublimated away if you have enough radiation. You can get cold. So all these paths of planetary evolution have these potentially observable, different observable surfaces, and the planets of our solar system sort of represent these several categories, right? We have water and rock, that's Earth. We have ice planets like the Galilean satellites, Europa, Callisto, Ganymede, or Enceladus. You have cold rock, which would probably be something like Mars, or you have hot clouds, which is like Venus, and you have hot rock, which is like Mercury. And so, in our solar system, all of these individual worlds they are interconnected, right? So we have, and that speaks to the evolution of the solar system itself, right? We have, an apparent increase in the minimum size of bodies with heliocentric distance, and we're talking like small bodies here. We're talking about the asteroids. We're talking about the main belt asteroids, near-Earth asteroids, Centaurus, Kuiper belt objects. As you go farther out, the minimum size you can see is larger because of the observational bias, right? It's harder to see smaller objects farther away. And there are similar biases, of course, as you search for exoplanets, right? You're only going to find, you will only most easily find smaller planets, Earth-sized planets, closer in, because it's harder to spot them from all the different methods as you go farther and farther away from the sun. And because our own solar system is imperfectly understood, our interior processes, our surfaces, we study those still largely indirectly. I mean, we've only walked on one other body in the solar system, and that's our moon. And so even Mars, which is the most studied other planet in our solar system, or Venus, which has had a fleet of spacecraft sent to it to orbit and some to land. Its atmosphere is better understood now than it has been, but we really don't know the processes that govern the formation of that atmosphere or that regulate it. Mercury is now one of the more studied planets in the solar system because of MESSENGER, and the European Space Agency's Bepi-Colombo mission is on its way there to add to that. But it's remote sensing. It is sending spacecraft there to study them as our proxies, and that is, of course, far and away better than we can do for any of the exoplanets. And it is what gives us our basis for comparison. When we know, or when we theorize what the processes are that determine have determined the atmosphere of Venus, or the evolution of the Martian surface, or the Mercurian surface, or even the gas giants or the ice giants. Those are informed in a way from the observations we've been able to do. They're informed in a way that we simply don't have available to us for non-solar planets. So the more we can do to understand the planets of our solar system, the better we can understand similar planets that, at least superficially, appear perhaps similar to those of our Earth. Because ultimately, again, one of the fundamental motivators of the search for other Earths. What are we really looking for? We are, yes and no. We're looking for other Earths. So clearly, this is one of our major goals. But we want to figure out how rare are we? You know, how unique is an Earth-like world, whether or not it has life on it, whether or not it's even habitable. How common is a planet in our type of zone of a given star? You know, we want to talk about, you know, we use the word, or people, exoplanet scientists and astronomers and all kinds of different people use the word habitability in a variety of different ways. And one of the I've been cautioned about a lot of exoplanetary astronomers about, you know, what does habitability mean? Habitability does not mean that there's life on that planet, or even that life could live. Life as we know it could live on that planet. So the definition of habitability is a question, right? It is, in general, when you talk to an exoplanetary scientist, habitability, sort of the habitable zone, describes a range of orbits around a star where a planet's surface could maintain liquid water given a sufficient atmosphere. Now that's great. I mean, that clearly describes Earth, but that also does not necessarily describe someplace you'd want to live, right? So when you think about habitable zones, it's a very broad definition. And if you hear, you know, in the news or anything like that of a planet in the habitable zone, that doesn't necessarily mean that, you know, you'd want to spend a vacation there. It does not, you know, necessarily define friendliness for life. And it also doesn't necessarily describe the only range of planets or only range of extrasolar bodies that would be amenable to life. We have potential environments even in our own solar system that are not that would not be described as being in the habitable zone, but may in fact be friendly to life processes, life chemistry as we know it. We have a number of the moons of the various gas giants, Europa, Enceladus, maybe even Callisto and Ganymede, maybe even Triton, where we know that under the ice layers of the surface there are liquid water oceans, right? So we don't know that we don't know anything about those oceans except that they have liquid water. We don't know whether they are amenable to life. We don't know whether there's sufficient chemistry, but those kinds of environments are environments that might describe a habitable environment. And there might be other niches. You know, one of the hopes still for life on Mars is not on the surface anymore, because that's very inhospitable, but perhaps in buried hydrothermal systems where there's still interior heat and still water, or even, you know, one of the places that is most it's ironically the most Earth similar atmosphere in the solar system happens to be about 55 kilometers above the surface of Venus. It's where the air pressure, the atmospheric pressure, and temperature are the most Earth-like of anywhere else in the solar system. Granted, the air is carbon dioxide and has very little oxygen, and granted that area is right inside the sulfuric acid cloud layer, so it's not hospitable, but it is the most habitable in that interesting way. So again, you know, this is why, you know, going forward, if you hear the term, you know, habitable or planets in the habitable zone, you know, take it with a bit of a grain of salt, because really it's the habitability question really talks about, is liquid water possible in that area, and you know, it's important, of course, for life as we know it, for life processes as we know it. But it is not the be all and end all. It is, however, you know, one of the fundamental bases of life as we know it. And of course, you know, in order to get life, we need water. We need essential elements, the chnops, right? The essential elements that, you know, that make our life processes possible. And you need energy. So, you know, the energy of the sun. You need biological chemistry. So, you know, all life on Earth has evolved and still exists, and it is highly varied, but still in a highly constrained system. And I tend to think that thinking in terms, and a lot of people do this, a lot of people realize that thinking in terms of Earth biology is pretty chauvinistic if you want to think about the possibilities of where life might actually also evolve. So there may in fact be, you have to expand your mind a little bit and think about, well, maybe water isn't the only thing you need. Maybe all you need is a solvent. Maybe all you need is something that can hold the chemistry that you need. So that if you have something like that, then you don't necessarily need to have water. You could have maybe methane. You could have maybe other things. You may be able to use other essential elements, and you may be able to have additional sources of energy. Right? We know on Earth that you can have life thrives at the bottom of the ocean, where the main source of energy is fumaroles. Right? This is vents from the Earth's interior. Right? So the Earth's interior heat is the primary source of energy down at the ocean floor. In the Jovian systems, it could be tidal energy. That's one of the reasons why the liquid water oceans exist on the Jovian moons, because of the warping and flexing of the bodies over time due to their orbits and resonances around Jupiter. So that is a potential source of energy as well. Let's see, it's not going to be able to see this. No, maybe not. But for now, we focus on the things that we can see the best, right? So all of these things are well and good. I mean, interior ocean, fumaroles, exotic chemistry under, say, the clouds of Titan and stuff like that. Those are all great and may actually be real possibilities. But in order to find something that we can see, we have to stick with what we know, and that's the light coming off of the planets that we see. So here's just a very quick tour of the inner solar system, and planets are all familiar. That's a terrestrial planet is composed primarily of silicate rocks, and this is also comparative planetology 101, right? We have rocks, metals, solid surface. So these are what we call telluric or rocky planets. They orbit relatively close to the sun, relative to the rest of the planets for sure, having few or no moons. They have similar interior structures. Each has a dense iron core, silicate mantle, and crust. The rocks exist mostly as a solid near the surface, and they feature all these different tectonic features like mountains, volcanoes, plains, valleys, impact craters, other formations. And when they have atmospheres, 3 of these 4 planets have atmospheres. They are secondary atmospheres generated through volcanism or cometary or meteoritic impact. So they're not sort of primary accretional atmospheres or anything like that. And here's just a quick view of even though they're fundamentally similar in their features, they're certainly different in their interiors. Mercury is basically a big core with a little rocky mantle sort of wrapped around it. Venus, we don't know very much about the interior, but we know it has a core probably like the Earth's, although we don't know if it's we don't know what the solid or liquid core might be. We don't know much about what drives its tectonic processes. Earth we know a lot about from seismic studies and all kinds of other things. We have our solid core, solid inner core, liquid outer core. We have our dynamo, which makes a magnetic field. Mars has a core, very only a bit of remnant magnetism. The general recipe of the terrestrial planets is similar. Let's see, let's jump ahead. So yeah, again, some basic statistics about the planets. I'm not going to go into it too much, but they're mostly circular, slightly elliptical, not very inclined. But one of the things to think about, this view of Venus is the view under the clouds, right? This is when Magellan, the Magellan spacecraft, was a radar spacecraft, flew in the late 80s, early 90s. It was able to, with radar, look through the clouds and see the surface, so we could see the surface comparatively. The way you actually see it from with your eye or with a telescope tends to be you see the clouds only. You see the atmosphere. You don't see all that cool stuff on the bottom. You don't know necessarily what goes into making that atmosphere. You just see the atmosphere. Earth, you can see through mostly its atmosphere, except for the clouds. Mars, you can see through its atmosphere. Mercury doesn't have an atmosphere. But if you were to back off, like way, way off, and go, say, several light years away, 29 light years away, like to TRAPPIST, the TRAPPIST system, which is where a few years ago we observed that TRAPPIST has, what is it, 6 or 7 planets? But if we could go, say, 29 light years away and look back at Earth and see the inner planets, they would be essentially single pixels, single spots of light. And instead of all this detail that we would see, this is what we would see. And each pixel represents a spectrum, right? So if you have a spectrometer, you can see that one spot in all these different wavelengths of light. You could do something, and these different colors represent varying spectrums. So you could tell the planets are different from each other. But what else can you tell, right? That's not necessarily very much, unless you get into the details of what the spectrum is telling you. These colors may or may not be unique. They may or may not be diagnostic. So, so thinking about that, right? We're thinking about looking at the planets, the terrestrial planets of our solar system. This is also just a look at 2 other solar-like systems, right? So we have the TRAPPIST system with its 7 planets. Here, the TRAPPIST star is a red dwarf star, so it's much, much smaller than our sun. And the entire solar system of the TRAPPIST system is within the orbit of Mercury. And for comparison, here's Jupiter. TRAPPIST star is not that much larger than Jupiter. And the Jovian system is about the size of the TRAPPIST system. So the orbits of the Jovian moons really kind of represent how the TRAPPIST system works. Now, because the star is so much smaller, there are actually a couple of the TRAPPIST planets within what would be called its habitable zone. But they also, the other interesting thing about that is that the TRAPPIST stars, the TRAPPIST planets, really whip around its star. Right, the orbital period is single-digit to double-digit days for each. That's what the year of each of those planets is. Their orbits are faster. Every one of them is much faster than the orbit of Mercury, which is 88 days. So, right. So here we have 4 rocky worlds around a yellow dwarf. Here we have 7 rocky worlds around a red dwarf, and here we have 4 icy worlds around a gas giant. So this is another version of this beginning of this comparison. So and these are the questions. What can we detect? What can we learn through direct observation? What do we have to learn through inference? What can we learn by comparing, what we know best? And also, so what can we detect, right? This is a plot of it was once a current plot of known confirmed exoplanets. This is now obsolete by probably hundreds, if not approaching thousands. We have now 4,000 confirmed exoplanets, mostly from Kepler. We're still adding to the Kepler total. But now that TESS is online, TESS is essentially a telescope using the transit method to map the entire sky. And we're expecting many thousands of planets to be discovered using this method. At least the existence of planets, not necessarily very much about them. Maybe their masses, maybe other things, but maybe their periods. But we are in an era where this plot of planet mass and period is going to be. The clouds of data are going to get much denser very, very quickly. But our own planets. Venus, Earth, Saturn, Jupiter, we are, in a way, we're a little bit off the edge of the planets that have been discovered through the methods that we use right now. And these are, there's a whole bunch of methods, and I can talk about a little bit about many of them, but really you could have an entire lecture or even an entire semester dedicated to any one of these methods, because there's a lot of subtleties, a lot of ways, a lot of important things to describe when you're talking about how to determine properties of a planet from radial velocity or from a transit in front of the star. And I'm not gonna do that because they're all really interesting, but they also take a lot of time. But the point is, there are a lot of planets out there, and as we get more of them, there are going to be more and more that will begin to approach planets that we directly experience. And so we're filling in mass, and to some degree, many of these methods give us at least a rough to even to a detailed idea of what the mass of the planet is and the orbital period. But so why does size or mass matter? And to use our solar system as a guide, the larger you are, the more you end up looking like a Saturn or a Jupiter. Then down to Uranus's and Neptune's, Venus and Earth. You end up being both. Your composition is gassy to watery to a silicate type planet to an iron type planet. So what you are made of, what you can see about a planet, is often seems to be determined at least partially by how big you are, and that has to do with what you accrete as you grow as a planet. Again, this is another currently increasingly out of date, very messy plot of mass and radius and temperature of rocky worlds, right? So Earth, blue to green colors are hot, right? So that's temperature, surface temperature of 700 Kelvin or thereabouts. That's Venus. That's not very hospitable. 500 Kelvin down there. So Venus is here, Earth is here. Again, we are seeing a few planets, even in this old, outdated plot, that are in the right mass and temperature range not necessarily the temperature, but the right mass range to be called Earth-like or Venus-like worlds. And again, as we get more and more of them, we're going to see more and more across this range, and more that will be potentially our size. This is a really great. I apologize that every plot I'm going to show you, I need to preface that these are out of date. These are out of date, but that's because we're discovering things so fast. And if I were to update it, tomorrow, by the next time I gave a talk like this, it would be out of date again. But the idea of what the habitable zone is, again, it changes, of course, with the temperature, luminosity of the parent star, right? So if you have our solar system, I'm going to jump over here, right? Our solar system is represented here. Here's our sun. Venus is sort of inside the innermost habitable zone. This sort of yellow line describes where you have enough energy that you would, if all the water on your planet would eventually end up in the atmosphere, and eventually that would get so hot that you would end up putting all the carbonaceous rocks in the atmosphere, and you'd end up with an atmosphere like Venus. Inside here, you have what would be the habitable zone. Mars is, depending on on how you think about it, could be just inside the minimum greenhouse zone. So if it were larger, maybe it could hold, or if it had a magnetic field, maybe it would have been able to hold on to its atmosphere and still allow liquid water on its surface. But also down here, the TRAPPIST planets, again, smaller star. So this is not distance from the x-axis is not distance from the star, but it is sort of starlight on planet relative to sunlight on Earth. So there are a couple TRAPPIST planets that look like they are relatively in the same place that Earth would be. There's all kinds of other issues potentially with the habitable zone, because when you have a smaller red dwarf type star, you end up they tend to be much more variable. They tend to be much more active. Having things like a star that's going to flare every couple of weeks, months, millennia, that's also not going to be particularly great. Even if you have a habitable zone, you might be getting roasted by the star with regularity. Another interesting quirk of this is that all of these Venus-like planets they represent actually confirmed exoplanets as well. We have discovered far more Venus-like exoplanets than, meaning planets that are interior to a habitable zone, than we have discovered Earth-like planets. And that's also part of an observational bias, right? Because planets like Venus are closer to their star. They are therefore brighter. They are therefore, if they're larger too, they also exert a larger influence on the star. So if you're finding planets using radial velocity, the wobble those planets make on their parent star is larger. If they're closer to the star, so they have more reflected light off the star, or they occult the star a little bit better, so and more rapidly, so they are easier to find. So that doesn't say that there aren't more planets, moving to the right. It's just that they're harder to see. So it will be easier to find Venus-like planets than it will be to find Earth-like planets. That's just one of the challenges. And again, the difference between a watery planet and a rocky planet. Actually, when you think about it, Earth, here's Earth with one Earth mass. It's actually very dry. It's hard to think about Earth as being a dry planet. That's because most of the water that we own is on the surface. If you think about that, most of the Jovian satellites, even though they're much smaller than Earth, they have more water than Earth does. So if you think about a planet that's the size of Earth, or several Earth masses that actually has more water, you end up with a much larger, much wetter, much different atmosphere than Earth. You end up with something that may look more like a Neptune or a Uranus than Earth. Something that looks like that's relatively dry and has relatively little water might end up being water, the same amount of water as the Earth, end up looking very rocky. And so, what's the norm here? We don't really know. Most of the planets we've seen, most of the small rocky or potentially rocky exoplanets we've seen, have been 1.5 to 2.5 Earth masses, and that's again Kepler era stuff. So most of the Earth-like planets we've seen are really super Earths or super Venuses. Is that the norm? We don't know. We've found thousands of them, but again, we don't know whether this is, and we will be adding thousands more to that total. So these numbers are going to get better. But is a 1.5 Earth mass planet, is that a good enough proxy to go thinking about? Well, it's going to look, it should look Earth-like. It should have the same processes as Earth. It could have the same chemistry. This is because I tend to be a very Venus-centric guy. I'm on the Venus Exploration Analysis Group. I want to send a whole fleet of spacecraft to Venus. One of the things to think about as a digression, Venus is every bit as good a model of a terrestrial planet as Earth is. So if you really want, and they're easier to see. So if you're really looking for Earth-like planets, for the most part, what we're going to find is Venus-like planets. So there's a real argument there for understanding our Venus better, so that we can understand what we're going to be finding more of. But we really want to find planets like ours. So here's the question: what are we looking for? Again, I'm taking my bias now as a planetary scientist. I look primarily at surfaces. I look at the light reflected off the surface to study its composition, to study what's going on. And so for this little project that we did, I took this bias and just sort of ran with it for an intellectual exercise. Spectroscopy is a major tool to characterize the surface of the atmosphere, right? If you have a spectrum of the surface, you can begin to understand its composition, its mineralogy, the processes of change that are going on it. So if you can do that, and there are certain basic things that are the same and different on different planets, on different types of planets. So if you could imagine, if you could see the reflected light off of a variety of these exoplanets, how would you know whether you found another Earth or not? And so this was the basis for this project that we've been doing for optimizing colors for discriminating Earth-like planets. And this was actually framed when the project began in terms of putting on your science fiction hat and thinking about all the planets you may have read about in science fiction where people have lived. There's ice planets, there's forest moons, there's ocean-covered planets, there's desert planets, there are city-covered planets, and the occasional Death Star, which is not really a planet or a moon. Could you, so we'll play the imagination game for a minute and just say, all right, all these planets are there, and we, people can live on all these planets. They just look different. But is there any way, and there, if you think about all these, very, very varied, but habitable, and clearly habitable, or at least imaginarily habitable planets, and all the other planets that we might find, is there any way to reliably distinguish this variety from those that you can't live on? And so that's, we want to do it as quickly and expensively as possible, right? So you can do this potentially if you have a very detailed spectrometer where you can get the full huge range of wavelengths of light and figure out all the little absorption bands of all the different atmospheric gases and whatever is on the surface, whether it's chlorophyll or whether it's water or clouds and all that, or cities and stuff like that. Then that's great. But is there a simpler way to do it? And so we wanted to find out whether there was a way you could do it. Maybe you can do it with just 3 colors. Or could you? That was the question we wanted to ask. And we started looking at our own solar system. And this is an augmented plot from a paper from 2011 where the telescope from the Deep Impact Mission spacecraft was used, the epoxy telescope, was used to look at a variety, most of the planets of our own solar system, in 3 broadband, well, several, but here's a comparison of 3 broadband wavelengths. There's an ultraviolet wavelength. Each of these bands is 100 nanometers across, and there's one in the ultraviolet centered at 350 nanometers. There's one in the visible centered at 550 nanometers, and there's one in the near infrared centered at 850 nanometers. So what this group did was it took ratios of these 3 wavelengths. So the y-axis here is ultraviolet over visible, UV over vis ratio. The x-axis here is the infrared over the visible ratio, so infrared light reflectance over visible, and plotting all the planets on it. So here's Mars, here's the Moon, here's Venus, here's Jupiter and Saturn, here's Neptune and Uranus on the left, and here standing all by itself, where the ultraviolet visible ratio and the IR visible ratio are both above 1, is Earth. So, and that's a cool thing to see. The Earth actually, at least in our own solar system, stands out from everything else just using 2 simple color ratios. Interestingly also that the ice giants, Uranus and Neptune, almost are by themselves as well in this other high ultraviolet ratio region. So it may be very easy. And so the first thing you ask, maybe it's very easy to determine an Earth-like planet from not Earth-like planets. So we added a few more things just to begin, just at the very beginning for the comparison. We added, forest-covered planets, a planet covered by oaks and by firs that has an IR wavelength off the scale, IR ratio off the scale. But if you don't put an atmosphere on, it doesn't fit in the same quadrant. But if you add a tree-covered planet with an Earth-like atmosphere, there it is in the blue planet area. If you cover a planet with water, but no atmosphere, you end up with looking something a lot like Uranus. And these are just using models, right? But if you cover a planet with water and add an Earth-like atmosphere, you end up with an ocean Earth. So that's not exactly in the Earth in this same quadrant, but it's up here. So maybe it's not exactly a quadrant. Maybe it's a region of some other kind of region. So we were intrigued by, maybe there is a very simple color comparison of finding and discriminating an Earth-like world from all the others. So we digitized the data. This is just a re-representation of that. Oh, by the way, Death Stars, not really very good because they don't have an atmosphere. So they look a lot like metallic asteroids. There's Psyche, which is the target of the Psyche mission, which is a metal asteroid. WASP 39b is a super Jupiter, so it's a hot Jupiter, and it's an exoplanet, but it also is sitting there. It's basically spectrally very flat in this region, and so it's there. Of the few exoplanets we've been able to get these kinds of wavelengths on, they also, because most of the planets that we've seen are these giant planets, so the fact that they don't look anything like our Earth makes a lot of sense. And of course, Earth is variable. So one of the reasons why the Earth's error bars are there, yes?
What is this phytoplanet?
That is a planet that was covered essentially by phytoplankton. Okay, so it
Still has an atmosphere.
This one does not.
No,
So
okay.
this is just it's using basically the spectrum of phytoplankton
Okay.
as your proxy. So think of it as a sort of a scum planet. Right?
Okay. Scum planet.
Right, and so anyway, we were again. This was a very simple way of doing it, right? So
Sure.
we just took that spectrum and tried. And, I wanted to before I decided to move on to something a little bit more rigorous. Before I wanted to maybe I want to do like a water planet. I want to do one with quartz sand or this kind of sand, or maybe I just want to make a planet of meat and see what that is, right?
Yeah.
Before we got too crazy, we decided to go into some real.
So no hamburgers yet.
No hamburger planet. But what we did decide to do was we went to the Virtual Planetary Laboratory, which is, I think it's run out of Arizona, if I remember right. And they've collated a large number, 80, it's now more than, it's probably closer to 100, Earth-like or near Earth-like worlds, taking spectra from literature, observations, modeling, where they put them into a large database that we downloaded and started doing some comparisons with. And these are the spectra of the Virtual Planetary Laboratory database from about across the spectral range that we were using. They have recently added planets from that model the TRAPPIST system as well, and we are starting to incorporate those in our study as well. And here's just a small set of examples. So here's spectrum of Venus, spectrum of Mars. One of the TRAPPIST planets. This is sort of a model of the TRAPPIST planet that's in the habitable zone. If you imagine that planet is wet or has an Earth-like an Earth-like and cloudy system. So this is a model still. It's not actually an observation. But here's Earth, and here's a model of an ancient Earth. And if you take the three wavelengths of the previous study, this is where each of those planets sits in those wavelengths. And if you see Earth, it is low in the visible, high in the UV, and slightly higher, at least higher than the visible in the infrared. So that sort of U shape is what makes the ratios greater than 1 for Earth. And this die-off down in in the ultraviolet, that's ozone. That's ozone cutting off the spectrum. But the other planets of that we see, Venus and Mars, they clearly don't have the similar spectrum, and these three broad bands are enough to distinguish that. So this model TRAPPIST could in fact be considered Earth-like because it's slightly it's close to 1 in the visible and the infrared, slightly better than 1 in the UV. So maybe this model TRAPPIST would fit. But we wanted to optimize our wavelengths. Yes.
What's the TRAPPIST-1 dip and the Earth dip that are the same? What is that from? If I had the laser pointer, it'd be no, this one. This one.
Oh, that's probably an atmospheric absorption. I don't know what off the top of my head. I should, so I don't. Yeah, and you can sort of see that the model TRAPPIST is sort of modeled off a terrestrial analog atmosphere. So those are very similar because one is a model. But because there is this variability, that's one of the reasons why we wouldn't pick this region for a broadband. But you can see in the visible to UV ratio is actually improved if we shift those bands over a little bit from what they were, and Earth is now more strongly divided because this UV vis ratio is in fact increased. And when we do that, so now I've rescaled this because I'm taking all the planets that we were looking at from the previous study, and here, by the way, right next to Earth is the TRAPPIST aqua planet. And if we add in all of the planets from the virtual planetary lab, we end up with something a lot more like this. So all of the green planets are sort of the most Earth-like planets that the VPL has. The blue ones are sort of edgier cases. These yellow ones are much more. They're like really dense atmospheres and sort of out of the range. So instead of having the blue planet regions being that belonging to Earth, we end up with something a little bit more like an ellipsoid, where most of the Earth-like planets sort of live. Now we still get false positives and we still get some false negatives as well. So it's not a perfect thing, but you wouldn't necessarily expect that. And also of note, Neptune and Uranus occupy a fairly unique spot as well. They're again different from everything else. And if we go back and look at our science fiction planets again, all of them fit in this region. So a water planet is not in the blue region, it's in the violet region, but it's in here where all of the Earth-like planets might live. An ice planet is down here, Arrakis might be there, Trantor might be there, Forest Moon of Yavin might be there. So these are, it's an interesting way, and potentially an interesting way of honing down, maybe not uniquely discriminating an Earth, but maybe increasing the chances of finding an Earth-like world, or one that would be amenable to life as we might know it. This is just a reprojection of it in log-log space. Everything's easier in log-log space because you make this wedge instead of an ellipsoid. You actually get more of the Earth-like worlds, fewer false positives and fewer false negatives. So I don't know how to describe that shape, but it may be that this is the more likely to be Earth-like wedge, as opposed to this here be Earths. But it's intriguing, and it may be that we have a method of finding Earth-like planets, or discriminating them, or at least making it a better shot. So the question is, what kind of telescope might do this, right? I'm going to skip that one. And so what we're doing, what we're in the middle of doing right now is we're trying to at least, roughly describe what might be called a low cost, at least relative to JWST, or relative to things like LUVOIR, exoplanet identifier telescope, or EXIST, right? Can we find, if we can assume that we can see the reflected light of a small planet. Now this is another caveat, right? Let's say we have an Earth-like planet 1 AU from the star that has 10% albedo, kind of like Earth. All these caveats. What would we, what kind of telescope would we want to build? We also wanted to make it a single detector, so that again, to make it as inexpensive as possible. We were talking about, we didn't necessarily care about. We wanted to see. We tested a variety of different variety of different mirror sizes and stuff like that, and we came across. We sort of came up with how long will we need to be able to stare at a given planet? Again, still ignoring the star for a moment. How long would we need to stare at the planet to get enough signal in these three wavelengths to determine what they were? So, and in this particular plot, we're looking at an Earth-sized planet and telescopes of 1, 2, or 4 meters in size, space telescopes. So, So if you could stare at the target for a whole day, you could see with a 4-meter telescope, you could see an Earth-like planet up to 40 light years. If you only had a 1-meter telescope, you can see 10 light years. So in order to see an Earth-like planet, 26 light years away, you need a whole month of staring at that one spot. So not easy to do. But you can also do the same exercise thinking about larger planets. So you fix the telescope at 1 meter, which is easier. Well, still a 1-meter telescope in space is not easy, but and instead of looking at necessarily Earth-like planets, now we're going to look at super-Earths or even sort of mini Neptunes. So for a mini Neptune, you can look out and see, out to 40 light years in a day. So that's potentially interesting. Maybe a Pathfinder telescope could which would not be impossible at 1 meter, could survey the sky out to 40 light years over the course of a couple years and survey Neptunes, which we know we can discriminate relatively well using just this broadband. So that's an interesting one. But we could also think about, what if we had even larger telescopes at our command, but we had to do it from the Earth? So, and we managed, we took a minor adjustment to our wavelengths, because we know that Earth in the UV is very UV absorbent, so we moved our wavelengths a little bit longer and assumed that they could operate the same way. We're still investigating whether that's a good idea. But if you have 30 and 39-meter telescopes, and we use this size because these are some of the planned next generation giant Earth telescopes, you could potentially see an Earth-like world or a Neptune-like world in minutes to hours of observation time. So this all does beg the question, though, of whether you can resolve the planets, right? Because they're still orbiting right next to these giant bright stars. And so it was described to me that really trying to see the reflected light off of the planet, it's like trying to see a firefly right next to a giant Hollywood searchlight pointed right at you from 10 miles away, and the firefly's off, right? So that's a hard exercise, blocking the light of the star, and that and there's a whole another series of talks you could listen to about star shades and how to block out stellar light using the star shade, or using coronagraphs to do it at the telescope itself. Those are extraordinary complex and really interesting and exciting endeavors, which I know the very beginnings of. But we're thinking about, if you can do it, if you can use those things and discriminate the stars, mask out the stars, then this is potentially something that would be interesting. The other thing that you can begin to do, is try to translate this broadband idea from reflected light to transits, which is again the most common way of identifying and characterizing planets currently. Instead of looking at the reflected light off the star, you see this as the planet passes in front of the star, its atmosphere changes the spectrum of light of the star ever so slightly, and you can extract that using a sort of complex analysis, and you might be able to do that kind of extraction again using broadband wavelengths. So, we are also trying to see whether or not we can talk to the folks working on W first to see whether we can add a UV filter to some of their instruments, whether or not we can work with them on their shorter wavelengths to see whether or not we can play this kind of game with the telescope that's actually being planned. And oops, I'm going the wrong way. And I think, and this is sort of where we stand. We think that there is something there, especially when you add UV light into the equation. That 3-color exoplanetary discrimination is possible and may even be useful. There are unique or near unique Earth optical colors due to atmospheric oxygen, nitrogen, due to land masses, and our mix of water and air. And we found, we've optimized these filters that may help us diagnose Earth's And Neptune's, with the exception of potentially pathological cases, you can have a planet that's very blue and very red from completely different processes as well, but there aren't that many of them. Or we don't, those are probably not very common processes. And we created a strawman telescope to search for these Earths and Neptunes. And we're trying to fill that out and talking to the current sort of next generation exoplanetary astronomers to see where this kind of synergy is useful and whether or not it makes sense to do this as an add-on or as a pathfinder or as something that would be helpful to discriminating the thousands of exoplanets we're beginning to find. So that's what we're doing. We're continuing the study into this summer, where we're going to build even more sort of variable spectra. We're going to explore those pathological cases and see where it leads us. And that is my talk. Thank you very much.
From a sociological standpoint, I presume you were an AGU member?
Yes.
For a long, long time.
Yeah.
And probably not yet a AAS member.
No.
Okay.
Yeah. Well, I was at Exopag just before AAS this year for the first time, so I may be joining soon.
Okay, interesting.
Well, so what kind of features on exoplanets would cause higher infrared emissions or reflectance? Well, a rocky planet will have a higher infrared reflectance than visible. If you think about the surface of Mars, one of the reasons why Mars is red or butterscotch color because of iron oxide, right? So, and that gives it that's a reddish spectrum. So essentially, that kind of an oxidized surface will tend to be have that kind of, or weathered surface will have that reddish slope. Yeah.
Why did you limit to only 3 bands? Like the 4, 5, maybe 6, if you more discriminators, while
Yes.
not greatly increasing the observation time?
Well, the question is, we wanted to, the beginning of the exercise was we wanted to see, could we do it all in one detector that would have a minimum filter set, right?
Okay.
If we could do it with 3, we didn't want to make it more complicated. Because you can always add more, but the more you add, the closer you come to an actual spectrometer, right?
Sure. Right.
And the idea being that if you can do it with 3, maybe you don't need maybe having simple radiometers or photometers may even be easier than having than having a camera system or having a spectrometer system. So it was really, again, we're trying to be as simple and in the end inexpensive as possible. Because if you want to build a space telescope, you're already not inexpensive, right?
Just a launch.
Right. But and it could also be that if the difference between a spectrometer or in 3 bands and 4 bands is small relative to the cost of the whole mission, then that could add some acuity, could add better definition, better resolution, more light gathering power, something like that. But the trade becomes, well, could I, for that couple $1 million, could I up my mirror size by 10 centimeters or something like that, right? And get more photons in total per wavelength, or more photons across more bands. That's the trade you have to do. And eventually we might go there, but if we can continue the study.
Are there any other questions? And I have a couple.
Yeah.
Do most rocky planets start out with CO2 dominated atmospheres? Because the Earth is special, presumably because the collision that produced the moon got rid of our CO2 atmosphere, allowed us to develop this nitrogen, oxygen, and
That's a good question, and I don't know whether we really have an answer to that. I mean, I think it's not really clear whether planets like Mercury ever had much of an atmosphere, right? And it's a terrestrial, it's a rocky planet.
Yeah.
So I think that not all of them do. It's also not clear what Venus's early atmosphere was like. Venus's early atmosphere may have been a lot more like Archean Earth's, which again, it might have been CO2 dominated, might have been water vapor dominated. There was probably liquid water on the surface of Venus for 1 billion or 2 billion years. There was probably liquid water on Venus's surface for longer than there was liquid water on Mars's surface, before its runaway greenhouse took over. But I'm not sure whether we could say what that atmosphere was. It probably was CO2 dominated, but unless life was there on Venus too, in which case, who knows?
The other question is, as far as the probability of finding habitable and Earth-like planet, what is the probability of a planet having a liquid core that lasts long enough to keep a dynamo that protects it from the stellar wind?
That is another great question. There's another angle on the habitability question, because there's a group of there's a non-trivial group that argues that you must have a magnetic field in order for life to be possible. You have to have the protection of the atmosphere. The magnetic field protects Earth's atmosphere being ablated away by the sun. It also protects life on Earth from solar radiation, solar particles. And you would need either a very thick atmosphere like on Venus, for example, but that brings its own problems, to protect from that, or to prevent enough loss. And we don't know. We know virtually nothing about the dynamics of any exoplanet, right? And we know very little about the dynamics of Venus. So part of the question, again, this goes back to the comparative planetology question too. We need to understand more. That if Venus had been a little bit different, could it still be a warmer version of Earth now, right? What's going on in Venus's interior? What is driving? There is not a planetary magnetic field for Venus. Is that one of the reasons why it's not Earth-like now? What is going on in the interior of Venus? We don't know. We have the capability, we have the technology to learn more about that, but it would require getting to the surface of the planet, doing some, which is hard but doable, and it would require more study. But one could argue that in order to understand what might be happening on the exoplanets, we need that, because this is what we have right next door. Same thing with looking at the ice giants, understanding how they evolved, how their atmospheres came to be the way they are. Why is Uranus on its side, right? All that kind of stuff. What are their magnetic fields really like? Because when Voyager whipped by, it went through and found all this neat stuff, but as a single point of observation, right? So that's not really enough you want to hang your hat on.
Well, let's thank the first speaker again.